Okay, this is the kind of next part of the course, which is maximum flow. It's a good starting point to linear program, which is like even bigger topic. But maximum flow is like a nice topic that is still about graph. But you see by like next class that it's really general. Like once you can solve this, you can solve 10 more or 20 more problems. Like, okay. And this is actually my research topic. Like I still really like excited up to work on this stuff, and you see what it is now. Okay. So what is this problem? It's a problem where you have a graph G, and you have a a special node, source node S, and sink node T. Okay. And each of like for each edge, you have some number which we call capacity. Okay. And the way you should think about this problem is that you want to kind of send water, like a flow of water from the source S to sink. You try to send flow from source to sink. Okay. And like you try to send this water from source to sink as much as possible. But you need to respect the capacity on each pipe. The edge is like a pipe. Okay. Okay. And so what does it mean to send flow? Then it to capture this intuition, you should think like for every node that is not a source and sink, right? You have that the amount of water that's sent through it is the same as the water that leave it. Like this should be like the rate of flow. Yeah, like if you send this water at the rate of 1 through here, then it should go out with rate 1 from the same node. Okay, but yeah, like water need to respect capacity. The water through each edge can exceed the capacity. And the goal is to maximize the amount of water that you can push from S to T. So let's try to, like this is like an intuition, the physical intuition, and it might help you. And let's see, for example, this is like one example of flow. Okay, I send flow 20, like with 20 unit through this edge. Then through this node, it must go out with 20 unit. Okay. For this one, I send through 40, then it must go out 40, like which is 25 and 15. So you need this flow conservation. In and out are the same. And also, the amount of flow on each edge need to respect the capacity. Okay. So just to get some intuition, like this is like a simple graph. And you can see that in this graph, the amount of max flow should be 2. Right? How? Well, you can just send 1 unit of flow here and 1 unit of flow here. Okay. And why the max flow value of this graph should be 3? Can you tell me? Yeah.
So the top one, you can send 5 at first, but then it gets cut down to 1 on the second edge. And on the bottom one, you can send 10 second, but since you can only send 2 in the first place,
right?
It's basically the max of, the min of each edge weight on both paths.
Very good. Yeah. Yeah.
So for these questions, we assume like at the source point, we have basically infinite water.
Yeah. Yeah. You have infinite amount of water from the source, but you just want to send out of the source as much as possible. Yeah. Exactly. That's like what Scott said. Here you would like to send here, but 1 is like a bottleneck. So you can send just 1 unit here. For this route, you can try to send as much as possible, but that should be just at most 2. So in total, you send like you can send 3 units. Okay. How about this one? Well, like you don't need to use this edge and just send 2 units on the top and on the bottom. That's like why the maximum flow is 2 here. Just ignore this edge. It's not useful. use this. Okay. All right. So, and then there is this example that of the flow that is not maximum, but it's a flow, right? This one that sent through an edge like this. This is a valid flow because each of this one I use 1 unit, but it just have value 1. But you know that you can send flow 2 units in this graph. Okay. So that's like a intuition, and here is a formal definition. Okay. So when you think of the flow, you think of like it's like you assign the value into each edge or into each vertex pair, right? For each vertex pair, you assign some value into it, and we say that the flow is feasible if the following is true. First, you need to have capacity constraint. You respect the capacity. For every edge, for all UV, right, the flow value on U, the flow value from U to V need to be at most the capacity, right? So it means that, for example, if U and V is not an edge, capacity is 0, so you cannot send flow from U to V if there is no edge there. And the next thing is just flow conservation. For every node that is not node U, that is not source and sink, right? You need that flow into U, which is the sum of flow into U here, need to be equal to flow out of U, which is the sum of all flow from U out to any node X. Yeah. So it's just like, this is just formalization what I said. The flow is just like assignment to edges of vertex pair such that you have 2 things, flow conservation and like you respect the capacity. Yeah.
If you're bottlenecked though, won't the flow out be less than the flow in? Like, in the one you had before, it was like 5 into 1, only 1 out. So wasn't the flow out 1?
Good question. So like in this example, right, I would actually, like the flow that I send here will be 1 and 1.
Oh,
Yeah. Here will be 2 and 2 here. Yeah.
This is sort of similar vein of question. Is that second condition, I guess, what does that accomplish? Because like I understand that it says, okay, you have to send 1 in and then 1 after, but I feel like it seems to me that if you just said, okay, you can put maximum capacity, but you can only send out however much the edge or the capacities of the outgoing edges are, it seems to me that wouldn't change the problem statement. Is there an example where that actually matters?
So like basically we kind of want to really find this object that kind of respect our intuition of water. So like if I said that I just assign 2 here and 10 here, then it really does not like kind of respect our intuition that like if I send 2 into here, I cannot generate like 10 unit here.
No, sorry, I was more so saying like, why couldn't we say I send 5 and then I can only keep 1, like in the top row?
Right, because we still want to, like for here, right? We still want to say that like if you use 5 unit here, like every unit of water need to go somewhere. It just cannot just say that, you cannot just say that it's just stop here. Yeah, we want to say that like every unit of flow that we send need to finish at the sink. Yeah. Does that answer your question somewhat or not really?
Yeah, a little bit. Maybe I'll see. I'm more so asking why that condition is necessary in the problem statement, but maybe I'll see that later. With examples.
Like, okay. So the goal, like right now, the problem statement really is to compute this object. This is like, that's how we formalize the problem. We want to find f such that this 2 condition hold. Okay. But this is like a two key condition of what it means to be a flow. Flow conservation and capacity respecting. Okay. There is another one that just for notational convenience, which is skew symmetry. So what I mean here is that this is just kind of for notation. I just gonna say that flow from U to V is basically negative of flow from V to U. This is to kind of, and this makes intuitive sense because you think of flow as is the water that have direction, right? For each edge from U to V, if you send flow with 1 unit from U to V, it's from V to U, it's -1 unit. Yeah.
So there can't be any bidirectional edges in problems like these?
Let's assume that there is none.
Okay.
Yeah. Right. But if there is two edge like this with, let's say, capacity 5 and this is 3, instead of having assignment from vertex for each vertex pair, I would have assignment for each edge instead.
Okay.
Make sense?
Yeah.
Yeah. But for now, let's assume that there's no bidirectional edge for now. Okay. So for this example, you can see that, if this is a graph and this is a flow where every, all of these purple edges have 1 unit of flow. Okay. So the flow from U to V here would have 1 unit. Capacity is 1. And so, what? So it does respect the capacity. Okay. How about the flow from V to U? From this direction, it's -1 because you actually send from U to V. So this is -1, and that respects the capacity as well, right? Because the capacity from U to V is none, it's 0. And yeah, the flow directly from S to T is just 0 because there is no edge from S to T. Okay. Some more terminology that makes sense. I just gonna say that an edge E is saturated if the amount of flow on E is just full capacity. It's saturated with its capacity, cannot send any more flow. Otherwise, we say it's unsaturated. Okay. What's the value of the flow? The value of the flow is the total of flow that go out of the source and minus the total flow of flow that go into the source. So it's a total net flow that you send from the source. In this example, flow out of S is 1, flow into S is 0, because there's even no edge into S. But in general, there can be some edge into S, and what you want to the value of the flow is the net flow that go out of S. What is the net flow that go out of node U or any node that is not S and T? It's going to be 0 because you have flow conservation. Okay. And because every node that is not source and sink have net flow 0. So the value of flow is just the net flow out of a source, which is the same as the net flow into the sink, which is here. Okay. Right. So that's now, I can state the problem definition precisely. We want to compute this flow. We want to compute this feasible flow that has these properties, and we want to maximize the value of the flow. Question about the problem statement. It's a lot of build up, but it does capture some intuition. Okay. So let's try to attempt to solve this problem. Okay. The first attempt is to do something that is not working yet, but it will motivate us to the new concept of residual graph. Okay. And the first attempt is just to be greedy. Okay. So what I mean here, let's start with like a empty flow, like I just assign 0 flow for every edge in the beginning. And what I'm going to do is this. I'm trying to be greedy. Just try to find a path, ST path, from source to sink in G, such that the edge on every edge on this path is not saturated yet. Because if it's like some edge on the path is saturated, then I cannot, it's like there is bottleneck, cannot do anything. But try to find this path such that every edge is not saturated. Then once you have this path, then you try to send flow along the path, right? So let's say that F prime is like the flow along the path that you can send as much as possible. And then just add this flow into your like solution F, and keep doing this until you cannot find any path like this, and then you return. And this makes sense, at least for example in this example. This is a good example, right? You find this path, ST path, yeah? This is not saturated, and you try to send maximum flow along this path. So send 3 and 3. And again, go to the next path. Like, what is the next path that is possible? You cannot do this anymore because this one is saturated. Well, just find another path here, right? And then you send, what's the maximum flow that you can send here? 10 and 10. So just send 10 flow here. So that's a good example. This is a bad example though. Why? Because here I just want to say that I've tried to find some ST path that is not saturated yet. I might be like, I don't know, stupid. I just find this one. Yeah. So go here. And once I do this, then like this one is now saturated. This one is now saturated. No like unsaturated path left. So I can just send one unit, which is not good. You have some suggestion? What should I do? Like, is there like some criteria to find a good path? Yeah.
I mean, this might be expensive, but finding the maximum flow or finding the like minimum number of edges used would at least solve this problem.
Yeah, like
I don't think that would
shortest
work in
path.
the general case. Yeah, but
Yeah.
shortest path.
Yeah, like in this, yeah, good. It's actually a good intuition, and it will lead to one good algorithm actually. So Scott said, what if we find shortest path? Which is not going to be good in this example, yeah, right? But it's going to still have some bad example, like this. So you can send float. This is the shortest path. But once you use the shortest path, then it kind of block these two paths here. So like the point that I want to make is that like trying to choose a path such that it will not block anything in the future is kind of hard to come up with. So that motivates us to try to basically maybe how about try to allow ourselves to cancel what we have done from the past.
This is just a quick question. Can there be, I don't know if you already said this, can there be cycles in this graph or no?
There can be in general. Yeah. It's just all of my example is quite simple and there's no cycle, but there can be. Yeah. Good question. Okay. So you see, like, we might make mistake, but what if we allow ourselves to correct our mistake from the past? That would be good. Okay, so we want to kind of cancel previous bad flow, like that one. And the idea is this. Let's say I try to do this, and I just try to kind of just cancel whatever I do here. Like it go in 1 unit here. I just go backward here and do this. And now this guy kind of get cancelled. Okay. This got cancelled. So you get to this one. Okay. Why does this make sense? It's like once you send flow in 1 unit here, it means that it allows itself to be cancelled by 1 unit in the opposite direction. Okay. In this example, we can try to do the same and cancel, and you get a good flow. Okay. So now the question is like, how do we formalize, like, to what extent can we cancel this flow on each edge? Okay. So that basically is what we need to formalize, and that is basically the concept of residual graph. Okay. So residual graph is this. So suppose that you have some flow on the graph G. This flow can be bad flow, not maximum one. Okay. The residual graph G with respect to F is just the same graph as G, but the residual capacity, like the capacity change. And it just said, like, it just define the capacity of U to V to be really intuitive one, just kind of remaining capacity of the capacity from U to V, just the capacity from U to V minus whatever you have used. Okay. So like you can think like a residual capacity CF UV is just amount of additional flow that could have sent through this edge without violating the capacity. Okay. So let's look at the example. This is a graph G. The red thing is the flow. Okay. And this is your residual graph. And what I want to note is that, okay, you can see that there is a reverse edge here. So for example, in this edge, it has capacity 20. So in this direction, right, the capacity in this direction is 15 because you have capacity 20 minus 5. Okay. But what about this edge? This edge has capacity 0, like from S to V, it has capacity 0. But the flow from S to V, the flow from V to S is minus 5 because the flow from S to V is 5. So this is the flow here is minus 5. So the capacity here is like 0 minus 5, so it's 5. And it makes intuitive sense too, because if you have sent 5 units of flow through for this one, then you can cancel itself by at most 5 units. The same is here. Now you have like reverse edge. Each has 5 unit capacity. Okay. Make sense so far? Okay. And by the way, like just for simplicity, like in residual graph, I will just not include any edge with 0 capacity. Okay. You cannot send flow anyway, remove it. So this is a graph with 0 capacity. Like this is a graph, this is a flow, then this would be the residual graph. Basically each edge here basically flip the direction. And you can see that in this graph, then there is a ST path, right? Which is this one. And this is exactly the path that can be used to cancel all flow and increase the like you can try to augment along this path and increase the flow value. Okay. Question up to this point? So with this, we are ready to come up with to show you an algorithm. And this is by Ford-Fulkerson from 60 years ago. And what it does is basically be greedy, like before, but do it on residual graph. Allow yourself to cancel what you have done badly. So this is a greedy algorithm. And what we're going to do here is just change it slightly to here. Okay. So it's just the same algorithm. As long as there is a path in residual graph, and this path will have non-zero capacity, right? Because I throw away all edge with 0 capacity from residual graph. Find a path in residual graph, send Maxflow along this path, like Maxflow along this bottleneck, like, and then add a flow, and keep doing this. Okay, that's the algorithm. Let's see how it does in action. Okay, so I start with like a graph here. Okay, in the beginning the flow is 0. So residual graph and the residual graph and the original graph are the same. Now I just find some path in the residual graph like this. Try to send maximum flow along this path. So it should be 5 here, because 5 is the bottleneck along this path. Send flow. 5, 5, 5, 5. Now residual graph is updated. Okay. So you update residual graph. Next, find a new path in the residual graph. What is the amount of flow that you can send? 15. So send that flow, 15. And then update residual graph. And so on. So keep fighting, update the flow, augment the flow. Find next path, augment the flow. Keep doing this. Okay. Can you still find a path? Well, there is one like this. And at least you can see that like we need to indeed like when we send flow along this, we actually cancel flow that we have done. So when to augment this, now you're gonna cancel this one from 5 to 0. Okay. So now there is no path from S to T in the residual graph. do you think that this value of the flow is maximum? Is there some convincing way, for example, to just maybe see from here that this flow should be maximum?
If you've saturated all of the edges going out from S, and you have that much flow at T, then it has to be maximum, right?
Yeah, like if there is this kind of cut here, right? And you know that any edge that go out of this cut are saturated. There's no way to send flow further. Okay. So this is actually maximum. That's like, for this example, just look at this cut. There's no way to send more flow out of S. All of them, all of these edges here are saturated. But it's going to be true in general that once there is no path from S to T in residual graph, the value of the flow is maximum. It's not clear why. We're going to prove it. Okay. Okay. So at least I hope you understand the algorithm. Let's try to prove correctness. Okay. Okay. So first of all, before saying that Ford-Fulkerson return like maximum flow, we need to say first that it does return a feasible flow, like a valid flow. Okay. So initially, like the flow is just 0, which is feasible, and then we try to prove this by induction that if the old flow was feasible, then after augment along some path, then the new flow is still feasible. Can you recall, like, what does it mean to prove that the flow is feasible? There are two things. There are two properties that we need to prove.
Capacity and conservation.
Exactly, capacity and conservation. Nice. So we need, okay, let me start with conservation and capacity. We need to prove these two things. Okay. So for conservation, we want to say that in and out flow for every node that is not source and sink are the same. Why is that? Well, for the old one, okay, for the old flow, it's true by induction. What about the new one? Okay. Well, the new one, like, is the new flow is just the old one plus the new flow that we augment, which is a path, basically. Right? This is like a F prime. F prime look like a path. And this path you send like maybe some unit, I don't know, like 10 unit. So you can see that for every node U in that is not source and sink, then like in F prime, this path, you will have in and out flow the same because you have in flow 10 and it must just go out 10. It's just you just augment along the path. So like in and out of F old and F prime are the same for every node that is not source and sink. So it means that like you must get like in and out of F new must be the same too. What about, so this is checked. Good. Next is capacity, right? We want to say that the flow respect the capacity. And so the intuition is this. The old one respect capacity by induction. And what do we do for this F prime? We try to send flow F prime, find this flow here, in the residual graph right? And when we try to send flow on the residual graph, it cannot respect the remaining capacity. So like you will not exceed the capacity because this guy that you add, try to respect the remaining capacity anyway. Okay, so let's try to prove this in like formally, right? F prime here respect residual capacity, remaining capacity. So for every U and V, you have that the amount of flow here is at most capacity minus FO. This is just the residual capacity of this edge with respect to FO. So it means that the value of flow from U to V, which is this plus this, it's just at most capacity. Just really intuitive. Yeah.
Sorry, can you explain for the flow conservation proof? I understand the two, like I understand why F prime and FO both maintain it, but can you explain again why
Sure.
why like when combining them or
Yeah, like so the inflow of F nu at U is just this guy plus this guy. And outflow of F nu is just outflow of FO plus outflow of F prime. So just add them up. Yeah. Okay. Good. So this we maintain feasible flow at all time. It's a valid flow. Okay. Next is we try to now say that when we finish, it is maximum flow. To do this, I need one new concept. Okay. A concept of ST cut. So new concept here. Let's say that A and B. I said that A and B is a ST cut if it's like a partition of vertex set into two sides, like this. Okay. It partition the vertex set here, and like, and there are disjoint, like they partition vertex set. Okay. And S is in A and T is in B. So it's partition S and T into two sides. Okay. This is ST cut. Okay. S is in A, T in B, and this guy partition B. And now the capacity, like or the value of this cut or the total capacity of this cut is the total capacity of edges only from A to B. I don't count edges from B to A. Like I just count capacity of this guy. I don't count the one that go here. Okay. So what's the value of this cut? 5. Yeah. Okay. So now there's one thing that we can talk about the value of the flow. I can say like one nice structural lemma, which is look at any ST flow F and any ST cut AB. I can say immediately that like I know for sure that the value of my flow is at most the value of the cut of an ST cut. Given any flow and given any cut, like every ST cut is like a bottleneck for every ST flow. Why is that? We're gonna prove this, but it's actually super intuitive. So let me start with like some intuition. Right? We have A and B, and okay, there can be like a lot of edges here. Doesn't matter. But let's say that I have 3 edges in total with unit capacity like the capacity, the value of this cut is 3. Okay. You know that like if you want to send flow from S to T, send flow from S to T, this flow must kind of consume capacity of this of the forward edge here. You might consume 1 unit, or you might consume 2 units like this. But each unit of flow that I send from S to T must consume some unit of the edge on the along from A to B. Yeah,
Does it have to consume all of them or just like at least one of them?
at least one.
Okay.
So every 1 unit of flow that I can send from S to T, it consumes at least 1 unit from the cut. So if I have 3 total capacity on the cut, then the total flow that I can send from S to T at most 3. Make sense? Yeah, that's like an argument. But let's try to like do this algebraically and prove it formally. So one way to prove this, and we will need this equation later. So let's try to look into this. I claim that like the total flow value, the flow value that I send, can be written like this too. That is a total flow out of a cut minus the total flow into the cut. What does it mean here? Just sum over all edges from A to B out of a cut, sum the flow value along this edge, minus the flow value in total from B to A, the backward one. Why is this the case? We're gonna prove this, but if this is true, then you can see that, well, this one is just at most capacity of the cut, like because of you have the flow like capacity constraint for every edge. F is at most CAB, FAB is at most CAB, and sum of this is just CAB. And this is at least 0. So assume this, then you get a lemma too. Let's try to prove this formally. Like let's try to prove this inequality. Okay, so like from the definition, you have that the value of the flow is just the value, like the net flow out of S, right? But then you know that for every node U on the cut on the side of A, which is not the source, the net flow are the same. The net flow is 0. In and out flow of U of every node in A that is not S is 0. So I can just add like 0 to all of this guy. I can sum over all A now. Okay. Is this good? With me here? Okay. Like I can just sum net flow out of U for every node in A now, because for every node U that is not S, this is just 0. Okay. But now when I look at this, right, then you can see that you can write like this too. Why? Because what do I do here? Like this is A and B, and like I basically compute. So let's look at an edge, the flow here, and here and here. Yeah. If I have an edge here, and I have some flow value here, it's gonna contribute like plus to one endpoint and minus to one endpoint. So it just get cancelled, right? Like it's gonna be inflow in one node, but outflow on another node. So it just get cancelled here. Which edge is the one that is not that doesn't get cancelled? It's just the one such that it has one endpoint in A and another endpoint in B. Okay. So the one that go out of A will not will give you positive number from this sum. The one that go in to A will give you negative value into this sum. So you get like a positive value of all of each flow along the edge that go out of the cut, and negative here along edge that go into the cut. Make sense? Okay, good. So we have this thing. All right. But anyway, like this is a nice, useful thing that you should know. Like value of the flow is just the total flow going out of the cut minus the total flow into the cut for any cut, for any ST cut. And keep this in mind. For any ST cut, it upper bound the value of the flow. Okay. So now with this, we are ready to prove that Ford-Fulkerson is the maximum.
Yeah. Sorry, I thought we just showed that the sum of that cut is negative. Isn't that what you just said? The sum of all the cut or the edges going from B to A is negative?
Yeah. Like for the flow value that go from B to A will contribute negative value in this. So it gives you this one.
Okay. Oh, but it's positive in the sense.
Yeah, it's like each of these term is positive.
Okay.
But it contributes negatively into this sum. So you have this one. Yeah. All right. So now here is like the famous. We are ready to prove the famous theorem. Like that's kind of the starting point of the whole area called combinatorial optimization. It's Maxflow-Mincut theorem. It says this. The three statements are equivalent. First, when you have that, the flow value f is the same as the value of ST cut for some cut. The next one is saying that f is the maximum flow. The third one says that there is no path from S to T in residual graph. Okay. Assume this. Assume that you believe this. Can you tell me why Ford-Fulkerson must return maximum flow? Anyone else? Yeah.
For every path, there'll at least be one edge that is saturated, so you can make the cut along that.
That is the case. You can make it like you can argue more directly. When do we stop Ford-Fulkerson algorithm? We stop when there is no path in the residual graph, right? Whenever we don't see how to go from S to T in the residual graph. But once that happens, then it means that f is maximum. If you assume this thing. Now I'm just gonna prove this, that they are equivalent. I'm just gonna prove 1 implies 2, 2 implies 3, and 3 implies 1. So let's prove 1 implies 2. Okay, so if well, you know before that, like for every flow, right? The cut upper bound, the value of the cut upper bound the flow. But it means what? It means that like if your flow actually like meet the upper bound, it means that it must be maximum, because you know that you cannot go further anyway. So if this is the case, then f must be maximum. Okay. Next, from 2 to 3, we're gonna prove contrapositive. So we're gonna prove that not 3 implies not 2. Okay. That is, I suppose not 3. That is, suppose there is a path from S to T in residual graph. Then you know that like you can find that path, and Ford-Fulkerson will increase that flow value. So f is not maximum. Okay, that's clear. So now I just need to prove from 3 to 1. Okay. So okay. 3 to 1. So suppose that there is no path from S to T in the residual graph. Okay. Like you said, like David said, like, okay, there is no path from S to T. Then there is basically a cut. How? Like I just define A to be like all nodes that is reachable from S in residual graph. I know that this set cannot contain T. Otherwise, you can reach T from S. Okay. So B is just a complement of A. So AB is the ST cut. Okay. AB must be ST cut because S cannot reach T. Okay. So now let's look at this. I basically define this thing to be like set A, this is set B. I cannot reach B. I can like there must be no edge from A to B, right? Because B cannot be reached from S. If there is an edge from A to B, then some guy can be reached here. There is no edge from A to B in residual graph, right? This is in residual graph. What if I ask you about like original graph? Can you tell me like for every edge AB from A to B in the original graph, not in residual graph, what's the flow value of this edge?
Cut?
Yeah.
Would it just be the cut? From A to B? No. Or like without the ones going from B back. Like wouldn't the cut from okay, so for our graph, that cut plus the cut in E of F would be equal to the overall cut, right?
I'm not sure I understand.
Like so we have from the first algorithm we have our flow, which we're not sure is totally maximum yet, and we've used up some of the edges, some amount of the edges, and G of F is the residual, and if you combined them, that would be like the total graph, right? And so wouldn't the cut from one we've made so far and the cut from residual be equal to like the overall cut? I'm just trying to say like okay, never mind.
Maybe let me ask you just like this. Like I just want to ask you like this specific question about one edge. Look at an edge. Let's say an edge from A to B, like node A to node B. And let's say that this edge actually is it goes from A to B in G. But in residual graph, actually, like this edge must be flipped. There's no edge from A to B. What does this mean? what's the value of the flow from this edge from A to B?
Capacity.
Yeah?
The capacity.
The capacity, exactly. Because if it's not reached the capacity fully, then this edge must still exist in the residual graph. So this must be capacity. What about the one that go from B to A? The flow value is what?
Negative.
Negative.
Like we've included everything that's positive totally. We've left out some negatives. Is that?
It's not negative. It's something else. Like let's say A and B to A actually is a edge in the original graph. Then yeah.
Is it 0?
It's 0.
Yeah.
Like the flow from B to A must be 0. Because if it's more than 0, then you will have residual capacity from A to B. Yeah.
Is it possible that after like the algorithms run and we have the final residual graph that there are multiple cuts such that it's only edges from B to A?
Yes, there can be many.
Okay.
Yeah. I will show like it's gonna be the case later that for every cut like that is a min cut.
Okay.
Yeah.
So if there's multiple cuts like that, then there are multiple min cuts
Yeah.
that are the same.
Yeah. Okay. But what do we have here is like everyone here is full capacity, everyone here is 0. But we know before that like the value of the flow, the value of the flow is the total flow out of the cut minus the total flow into the cut. This term is 0. This term, F here is just C, right here, which is exactly the capacity of a cut. So we complete that like a 3 implies 1. So if there is no path from S to T, then you can find a cut AB such that the cut here has like the value of the cut is the same, exactly the same as the value of the flow. Okay. All right. So with this, we get Maxflow-Mincut theorem, which is not just useful algorithmically, it's useful for graph theoretic sense too. It's just structure of the graph. For any graph, value of min cut is the same as value of Maxflow. And yeah, like, can you tell me quickly that given, suppose that I give you Maxflow, how can you compute a ST min cut quickly? It's kind of from here.
Are you also given the residual graph?
Yeah.
And then you just do the same thing where you find basically the furthest vertices you can reach from S, and those are A, and then everything else is B.
Exactly. Yeah, like suppose that flow F is maximum. There's no path from S to T in residual graph. So just find A, the set that S can reach. And we just prove that this cut, its value is the same as Maxflow. And so this must be minimum cut. Because this cut must be always, cannot go below value of Maxflow, right? But it does reach the value of flow. So this cut must be minimum cut in the whole graph. It's like the flow, you know that for any flow and any cut, the flow is like lower than the value of the cut anyway. And so once this thing meet, then that pair of flow and cut must be maximum and minimum guy. Okay. Okay. It's not quite clear though, like if you want to compute min cut, if you want to compute Maxflow, given a min cut, how to do that, I don't know actually. But given Maxflow, you can compute min cut easily. Okay, so next is like a running time of Ford-Fulkerson. Well, it's not hard actually. Like, you know that like the number of iteration. Let's say that the capacity of edges is integral. So the number of iteration is the value of the flow. Each time like you increase the value by at least one. And each iteration you just do like the first search to find a path in residual graph. So that's m time. So the total time is like m times the value of the flow. Okay. So if the edge has capacity 1, then the value of the flow is at most m, because like each unit of flow kind of consume 1 unit of capacity on some edge. Yeah. But so this is gonna be polynomial time if the capacity is 1. But in general, like this can be big. For example, like if you have this graph, right? It's a graph with 4 nodes. Let's say this capacity B is huge. What Ford-Fulkerson might do is it might augment through this one. So now like this is -1, and this edge is flipped. And you augment along this one. This is -1, this edge is flipped back. And keep doing this. So you need to repeat like B iteration, although the graph size is 4. It's not polynomial time. Okay. And even worse, like you actually can have the graph, if the edge is not integral capacity, it might not even terminate. It might run forever. That's possible, but I might put the example at the end, but I might not prove this. Okay. So let's try to get polynomial time algorithm. Okay. And that need us to define blocking flow. Okay. So let me define what blocking flow is. So we said that the flow F is a blocking flow if for every path from S to T in G, not in residual graph, in G, every path contains some saturated edge. Okay. That is, you cannot just push more flow from S to T along the path in G, not in residual graph. Okay. Like for example, this is like blocking flow. Right? You cannot find another path that is in G and that is not saturated. Okay. Can you tell me like how can you compute blocking flow? Any idea? Yeah.
I feel like if the original algorithm we looked at, where we were just looking at G and saying like pick an arbitrary path, like the original greedy algorithm, if you saw that couldn't continue, but the residual graph one could continue, then you know you have a blocking flow.
Yeah, exactly. The original one, the greedy one, is exactly the one that compute blocking flow, because it just try to keep finding a path in G that you can augment, right? So once you can augment with once you can find augmenting path in G, it means that this is blocking flow. Okay. It might not be maximum flow, but it's a blocking flow. Okay. Yep.
Oh, I was gonna ask about the greedy algorithm, but maybe you're about to cover it. Like, what if the greedy algorithm in that graph from before chooses the top path and then the bottom path, and it chooses 2 paths, neither of which are blocking?
Okay. So, like, if it chooses this path and choose this path, then it's a maximum flow. And any maximum flow is actually blocking flow too.
Okay.
Right? Like you just know that you cannot augment whatsoever, even if you allow yourself to cancel.
Yeah.
But like, so blocking flow is like a weaker thing than max flow. But if you get max flow, then it's a blocking flow as well.
Okay, I see.
Okay. Anyway, like this original greedy algorithm compute you blocking flow. Okay. Because just keep finding an edge in G that is like a path in G that is unsaturated and augment along that. Okay. Okay. So and okay, this is fine. What's the running time? I claim that okay, in each round, like what you can do is like when you find an edge that is saturated, now you can just delete from the graph. And in each round, you augment along some path, and you will just saturate one edge. So you will throw away some edge. So number of iteration here is at most m, the number of edges. In each round, you spend linear time, just do some depth first search. So the total time is at most m squared. In each round, spend linear time. There are linear number of rounds, m squared. You can actually improve this. It's in the homework. If the graph is directed acyclic graph, can improve this to mn. Actually, even linear time when the capacity is 1. But that's in the homework. Okay, so what's Dinic's algorithm? Dinic's algorithm is this. It's an algorithm that basically instead of trying to augment along one path, like in Ford-Fulkerson, it tried to augment along blocking flow. Okay? So what is this? Well, let's see. So you just look at the residual graph, and then I define a new graph, which is important. It's G prime. G prime is a subgraph of residual graph, such that it only contains edges along ST, like ST shortest path. Okay, so like look at if an edge is in some ST shortest path in residual graph, then put that into G prime. And this is like a shortest path in the unweighted sense, right? The capacity, like you ignore capacity, you do like breadth first search, and just compute like count the number of paths here, number of edges, ignore capacity. And then I look at blocking flow, compute blocking flow in G prime, and augment that, and repeat. So basically, instead of augmenting along one path, augment along blocking flow. Let's see example. Okay. This is a graph. Well, then what's the shortest path? Like what's the shortest path from S to T? Like what is the distance from S to T here? 3. You can go like a 3 hop here. This is not shortest path. So like the distance here is 3, and the bold 1 is in G prime. This guy are not in G prime. Okay. So we compute blocking flow in G prime on the bold edges graph with bold edges. So that's blocking flow on G prime, and augment it, and you get the new residual graph. That's one round. What's the distance from S to T here? It's going to be 4 now. Like the bold one is like the one that along some shortest path. None of other edges are in shortest path. So the bold one are G prime now. Is a look at residual graph and look at the edges that in some shortest path in residual graph. This is G prime. The distance is 4. By the way, like you see, distance increase. Okay, it used to be 3, now it is 4. It's going to be true that the distance keep increasing. Okay. Then compute blocking flow on this G prime. Augment that and update residual graph. Now there is no path from S to T, then you're done. There's no path in residual graph from S to T, then you're just done. Okay. So now the lemma that I just mentioned, and the key lemma is this. In each iteration, after you augment along blocking flow, the distance from S to T will increase by at least 1. I will prove this, but suppose that this is true. Do you see why this is like polynomial time algorithm? What's the maximum distance that can it be from S to T?
N minus 1.
N minus 1. Right, because once it's more than n minus 1, then you know that there is just no path from S to T, so you are done. So there's just at most n minus 1 iteration, assuming this lemma. And in each of the iteration, you just need to compute blocking flow. I need to tell you first how to compute G prime. Actually, G prime can be computed quite easily, but you compute G prime and you compute blocking flow on G prime. Blocking flow you can do polynomial time, so in total it's polynomial time. I told you how to do blocking flow in m square, but you can do it in mn actually. So the running time is this. Okay. So by the way, how do you compute G prime? How do you compute G prime? Like, how do you identify these edges? Yeah.
You could just set all of the weights equal to 1 and then do like Dijkstra's.
Yeah, Dijkstra or even breadth first search.
Oh yeah, BFS,
Yeah. So you do breadth first search, you're gonna get like the guy at level 1, the guy at level 2, and then you reach T. And only edges that kind of go from one level to the next level will be in shortest path. If it is in the same level or go backward, it's not in the shortest path. That's it, right? Just do BFS and look at edges that go from one level to the next one. So computing G prime, just do BFS in residual graph. So okay, so this is really polynomial time algorithm. Let's prove this. Okay. Okay. So I'm just gonna like define this graph. Okay. This is just a graph that is like I define level J to be all the nodes such that the distance from S to the node to that node is J. So S is at level 0, then the next guy is level 1, level 2. This is just the level from BFS. And you know that D is a distance, let's say that D is a distance from S to T. So G prime is basically the forward, like all forward edges in this graph, like the edges that go from level J to J plus 1. That's G prime. And what you do is to compute blocking flow on the green graph here, on the forward edges on G prime. The green graph is G prime. Okay. So I want to prove now that if the distance used to be d, once I augment with the blocking flow in G prime, and I look at the residual graph after augmenting, the distance need to increase. That's all I need to prove. This is the last lemma in this lecture. Okay. So this is what it looks like when I find blocking flow, right? And I augment. What happened is that like each of the edge that I augment here basically gonna be flipped. Or like I would just create some edge in the opposite direction of edges that I use. Okay. So one thing to note is that the new edge that I add is going to be always backward edges. Because I use the edge along the forward edges. I use only green one. This is the one that go forward along the layer. So the new edge that I introduce here only go backward. Okay? So can I ask, like, can there be, like, look at this graph. Okay? Can there be still some path that use only forward edges in this graph? It's not going to be the case. Why? Because this flow is blocking flow in the green graph. I cannot find another path that only contains green edges in this one. If there is one, then this flow is not blocking in the green graph. Make sense?
But we're not like for every edge that we're going backwards now, we're not deleting the forward edge that corresponds to it, right?
No.
Okay.
Yeah. So, like, no. Like, I actually make it, like, this is the one that, like, some of, like, if, look at this path, for example. One of an edge must be deleted.
Right, yes.
Because I make it, like, saturated.
Mm.
So if there is still some green path here, then it means that I didn't saturate all the green path before.
Okay.
Okay.
Mm-hmm.
So like this red flow, the blocking flow is blocking all the remaining green path. There's no like a path that's all green left.
Okay.
Okay. So now it means that if I find ST path in this graph, some of an edge cannot go forward because this path cannot only go forward anymore. Like there must be some edge that doesn't go forward. Okay, so it means that I might find some path, but at some point I stay at the same level or I go back one level. But if that's the case, then it means that this path must have more than d steps. Because this is the way to take the way to go from S to T within d step is to go forward at every step. But now I know that any path here cannot always go forward. It must go back or stay at the same level. So that's why like any path must have more than d step. So the distance increase. Okay. So I went over time, but that's basically complete the whole argument. Okay. Let me wrap up. What you just saw is that this algorithm, Ford-Fulkerson and Dinic, compute Maxflow. By the way, it does compute integral value flow. If every edge has integral weight. You can just see from the how it works. Like it maintains integral value. Never try to send like a half flow, right? So this is like gonna be useful in the homework. If it has integral capacity, there must exist integral Maxflow. And here is a state of the art. Here you see how to compute Maxflow in polynomial time. By now, actually you can compute it in almost linear time. That's super fast. It's not easy algorithm, but it can be done now. It has like little one in the exponent here. If you want like polylog, like I had like one work with my co-author, but it's not as fast. Like it has this term. Okay, and still there are a lot of like exciting development. Like last year, I still like try to get like a nicer and nicer algorithm on Maxflow. Okay, so the next time you see that once you can solve Maxflow, there are like 10 more applications that you can solve. Okay, see you next time.